Well, thank you all for coming out. I'm here to introduce my postdoc here since last March, Mathieu. Mathieu is Franco-Argentinian or Argentro-French, or however they call it, and he speaks 4 languages. So I'll leave you to guess what the 4th one is, and try it out on him sometime. His college was called a lycée. We don't know what these things are. He says that's sort of like undergrad science college. And then he went to a place called Estaca, which is a great engineering academy over there, for what is something like an MS, is the way it's explained to me. And the engineering mindset didn't quite satisfy him entirely, so he's got a physics mind, and so he decided he'd steer more toward physics, and he went off for a 1-year magisterium in physics at the University du Paris. That's sort of like a certificate on a master's, I guess, is the way I hear it. And that made him think physics was so great that he went off for a full-on PhD in physics at Paris-Saclay, the oldest university in Paris, a place called LATMOS. It's a center with a lot of atmospheric science research. And some fun facts, quadrilingual, also a naval reserve officer for another couple of months. So we hope France doesn't get into any naval battles that yank him away from the research here. But meanwhile, we'll be glad to have him working on atmospheric gravity wave observations.
Thank you everyone for coming. This is actually going to be my first talk on American ground, so I'm very happy to be here. I'm going to try something which is a bit specific. Since I've only been here for 6 months, I have some work to show you, but I'm also going to try and show my PhD work. So I'm basically trying to pack 2 subjects into one. Might be a bit, beefy, so there's 2 stories. You're not obligated to understand both, but I hope you'll get some interesting insights from each of it. It's going to talk about gravity waves, atmospheric one. I'm sorry for all you oceanographers. And we're trying to look at, I'm going to say, non-traditional instruments and data sets, which we believe, is a very interesting and unexploited goldmine for information in future research. Following Brian's very good presentation of myself, I will just add a tiny detail. Yeah, which is, indeed, I started recently, so that's me when in Paris, very typical. Then I flew to Florida to become a Florida man. But I want to point out, that there is some, link between both of these. Is I still work on gravity waves. Gravity waves was my PhD topic, and it still now is my postdoc topic. So what we're going to do is first go through my PhD story, and then I'll show you some early works we have going on with the postdoc. So I'll start talking about what this comes from. I had the chance to go many times to Athens during my PhD, more precisely in Monastiraki, which is very close to the Acropolis. Along it you can see many monuments, such as Hadrian Library, but the one that is less common and less known is called the Tower of Winds. What really struck me is, even back then, that means centuries ago, people already had an understanding and, I would say, an interpretation of winds. Back then, obviously, there was a real interest because of storms, agriculture, commercial streams, and most of the Greek and Roman war used to be maritime tactics. So there was a huge necessity for understanding. And what's interesting is they also came up with proto-classification of wind. That's Boré, which gave them the name boreal, and Ciron, which was the northwest wind. They were quite far from what we have today, but you can already see some credits to what they tried to understand winds in their own ways. A few centuries in the future, we have other towers of winds. This is Vega C, launched in Kourou in French Guiana, with its payload a very unique one, which is called Aeolus. Aeolus means the god of wind, and in this case, it's a wind observer satellite. So millennia later, nowadays, wind is still a major challenge to understand. It's not completely understood, but it's major to many topics such as weather forecast, wind energy, air pollution, and many more. What's Aeolus exactly? I'm going to try and picture the satellite very quickly. It's a very long and complex story because it's a satellite that was approved in 1999 but launched in 2018. That's not usually that long. It went through many trials and errors, and the point is, This is because it's basically having a space laser inside it. And many of you saw Star Wars. It's basically like the Death Star, only smaller. It is quite hard to function because it requires a lot of energy, a lot of precision. And I think NASA tried to draw something like this previously, but they just ditched the idea. So it was us Europeans that took on the mantle. It came with many expectations, improved the quality of weather forecast. But us atmospheric dynamicists also thought, well, with such coverage of wind over the whole globe, maybe we can try to advance our understanding of wave processes. And also, because it's the third of its kind, the idea was to demonstrate the power and the possibilities of having a Doppler wind lidar in space. So how does it work exactly? Well, you have this kind of system that basically shoots a laser downstream and gets the backscattering back. I'm not going to go into many details, but that's what we call radio diffusion, which means is you throw a, I'm going to say, UV light into the atmosphere, you can get the signal back. And based on if the signal comes a bit more red shifted or blue shifted, you can actually get the velocity of the wind. In our case, what's a bit inconvenient is we don't have a clear meridional or zonal component. We get a mix of the two, which is called H-loss. Because as you can see, we have a specific projection when we fly across the globe. And in our case, we're going to focus specifically on clear sky condition, which means no cloud, no aerosols, just plain wind, which means we're going to get radio diffusion. But keep in mind that satellite was also able to get aerosol retrieval through MIB channels. So just so you get the general idea, the way it works is you use two components, the Doppler effect, which probably most of you know, and the elastic molecular scattering, which means, in our case, with our specific wavelength and the property of the air, you're going to get a backscatter within the same direction, only changed based on the velocity of the object, which is the Doppler effect. That allows you to get the Doppler frequency shift, which means in the end you can get the velocity of the wind column you're looking at. We're also very lucky in my previous lab to have two historical objects which are the same exact principle as the LiDAR. Actually, the Aeolus-lidar is based on the principle we developed at LATMOS. So it's a very old expertise, 1985, but we're lucky enough to have them at very different places. So one in metropolitan France and one in the French island of La Réunion near Madagascar. And we were lucky enough to have 4 different campaigns, which mean 2 different places at different times. That's very interesting because we're going to be able to compare the satellite directly with the same functioning instruments, but at different times, both in space and I'm going to say health cycle of the satellite. Another important point is how the satellite looks at the vertical information. You have what's called a range beam setting. Aeolus is able to look at the wind column, but only a specific point. Then it does averages. There's only a set number of points you can have, and it's up to you to kind of decide what resolution you want. As you can see here, if you opt for a pretty big and high one, you're going to get coarse data on the upper layers, but you can also try and imagine maybe smaller and less coarse resolutions. The point is, we don't always have control of this. That's ESA, European Space Agency, that decides this. So you're basically going to have to do with the specific place you're in. So in our case, we're going to use a tropical RBS, but also other specific RBSs depending on when and where we use it. A small statistical comparison we managed to do was looking about the satellite and its results. Because, of course, before looking at gravity waves and make it science, we have to make sure it works. And as you can see, what's really interesting is you generally have a very good correlation here. So what you're looking at is the bias over the column, and the shading represents the standard deviation. You can see very good agreement, I'm going to say, between 5 and 20 kilometers. What's above is probably the lack of air density. So that means that the signal to noise ratio is gonna get less interesting. You're gonna get less backscatter, so you're gonna get less information. Same goes for the lower part. That's probably what we call cloud contamination, which means it's not really clear sky. There's probably some aerosol contamination, and that does mitigate the results. ESA had very specific mission requirements, so we decided to compare them with what we saw on our hand. And when it comes to bias, we are quite close to the expectations. But when it comes to standard deviation, we're actually, I'm going to say, 2 times bigger than what we should have. And that's a problem because variability is what we're going to look for in waves. And that's something we need to keep in mind. Bottom line is, if we want to stick to very reliable data, I think between 5 and 22 kilometers is a very trustable range of measurements. There's a French painter called Eugène Delacroix that said that we do not see truth in masses but in individuals. And I think what he meant is that it's also interesting to look at case-based studies to get a more intuitive understanding of how comparisons work. In our case, I picked 4 specific cases where we compare Aeolus with ground data. So blue is Aeolus, red is the ground lidar, and black is a radio sound we sent at the same time. So you have many issues appearing. The first one on the top right, it is kind of bell shape you can see here. That's typically, if you factor in that the shading you see here is the estimated error by Aeolus, that this is probably once again a problem of lack of backscattered signal. So that probably means there's not enough air density in that area. And the fact that the shading doesn't get even close to the real data means Aeolus is not really capable of diagnosing its own error in the higher, I'm going to say, altitude layers. Another interesting thing is this, what you see here. They all seem pretty good in agreement except at this specific point, which is what we call a hot pixel. You could see this as like a black pixel on your TV. It's a saturation from the ACCD captor. The point is that's going to get saturated probably in the next subsequent profiles for a bit before it desaturates. And while this is fairly easy to spot out, the problem is over time with solar activity and the signal lack of, I would say, precision, this got to be more and more present. Another thing, I was the first one pointing out is this very weird oscillation. In normal times, I would be very happy about it because that could typically be the signature of a wave around 2 kilometers in wavelength. Problem is, it's very weird because it's oscillating from one pixel to another and doesn't seem to be, appearing on the other 2 objects. So this is probably an instrument-induced oscillating perturbation. When I tried to point it out like this, Issa said, no, that cannot be instrument-induced, that's impossible. So I said, okay, I'm just going to call it OP for oscillating perturbation. Turned a bit diplomatic, but my guess is there is something somewhere creating resonance in the signal. And the last point is, you can always get a happy marriage of all these problems together when you have probably this oscillation appearing, probably a hot pixel, and also here a big shift between observation and Aeolus, probably because of the lack of wind. Okay, a few points before we really depart from here onto the science. We managed to do long-term validation of the data based on our ground measurements, but also on Météo France radio sounds. They launch twice daily radio sounds in specific sites that are quite close to Aeolus overpasses. So what we did is the standard deviation of the difference between radio sound profiles and Aeolus's profile. So basically, the value within itself has no real meaning. What's important is the evolution of that signal over time. Because there is no real reason for the data to be more noisy over time. There is no increase in dynamics. So that would mean that the noise from Aeolus is actually increasing. And that's what you can see here. You can kind of see over time, when they switched off to the first laser to the second one, a small increase over time. And then switching on to FMA, which was the first laser again, and through a couple of very good reprocesses, you can see how the signal tends to be evened out. The point is, the satellite is a almost living and breathing human being that has its own up and down, and you have to take that into account if you want to make long-scale climatology studies.
Sorry, I have one question.
Yeah, sure.
So what is showing the dot outside of the shading area?
Sorry?
The dots are outside of the standard deviation.
These points?
Yeah. Is it important or you are considering?
So all the gray points are the radio sounds one, and the other points are retrieved from our campaigns. So that explains why it's so low here, because it was really close to the satellite, and sometimes they get it really, really wrong for some reasons. Did I answer your question?
Yes. Is it important? Like you are considering as a noise? It's not important. Like what is the point here showing the standard deviation? Because you are, I don't know. I'm confused with the signal and the standard deviation.
Oh,
so what is the point of you are showing the plus minus standard deviation,
Yes.
and any point like outside of the standard deviation, what that mean? Like it is noise? You're not interested
Well,
in?
yeah, probably. So what I'm going to say is what you see here is indeed the standard deviation of the data. If it's outside, this is only comparisons. Chances are the geospatial biases were too big, which means the overpass of Aeolus was either too far away, or the dynamics, the one cut was very different from the other. So they probably are non-representative of the noise I'm trying to get of the signal. What's important is that we have a very clear trend appearing, which means I will need to account for it in the future.
Okay. Yeah, so, I mean, any data point can be outside the standard deviation.
Yes.
So those circles, that says mediofrequency collocation, so that's like a weather analysis?
Yes, so no, that means it was a radio sound launched by
Oh, it's a
Mathieu
radio
Ratynski.
sound. Okay, those
Yes.
are radio sounds. And the other two, what's the blue
So
line?
radio sound collocation and UN, which means lidar collocation, were made from our...
By your team?
Yes.
Okay.
Okay, so you can see why it's so low here, because it was very low geospatial biases. But then Météo France just launched them around midday and midnight, which is not always close to Aeolus, blah, blah,
Okay.
blah. So the point is, the one-to-one comparison makes no sense. What makes sense is looking at the long-term trend. And now I'm going to go back to wave retrieval. I realize I haven't really talked about waves. So I'm probably sure most of you know it, but there are many waves on the atmosphere as well as the ocean. And gravity waves is actually just a, I'm going to say, subcase of waves in the atmosphere. They come in many section sizes, but gravity waves are on the lower side of the spectrum. They can go from a period of a few minutes to several hours with quite big horizontal wavelengths, but actually very small vertical wavelengths, which is what we're going to get, and which is actually perfect because this coincides with the average size of the wind column we're looking at. You can kind of see here one type of generation is through orography, which would be mountains, but you can also imagine convection with very strong updrafts or even more complex interactions such as wave-wave or wind shear. So how does gravity wave is usually described is this kind of oscillation. Here's a very simple example of a linear theory system where you have this height of the mountain which dictates then the amplitude and the wavelength of the object. This is solved in linear theory and it can be parameterized based on the many factors. And you can actually even do non-holographic parameterization in models. But I have to mention that when it comes to non-holography, this becomes more experimental, more empirical, less driven by a, I'm going to say, very strong theory and formalism. There's also a way to show it as a picture so you know what it looks like in real life. And I even got lucky enough recently to get a picture of myself, so just, you know, it's not a hoax, it actually exists. Gravity waves are hard to find, but we can use many proxies. In our case, wind speeds, or you can even look at clouds and their movement relative to the overall system. I'm going to go briefly on the formalism. Point is, you have many physical laws that dictate how a wave can behave, and the main two factors are the Green bystander frequency and the Coriolis force. Basically, these two objects are going to create the boundary of your frequency. You cannot go above or below that. And then you can have all these wave numbers that's going to be dependent on, obviously, the objects you're going to use for your creation, as well as the scale height, etc. So that would be dependent on many factors, such as the air density and so on. That's actually a very difficult formula to work with, so we can find ways to simplify it. Since we're going to focus on very specific waves called internal gravity waves, that's going to be between, I'm going to say, a few hours in terms of period. So the formula itself simplifies itself to this much more usable formula. And what we can do is compare Aeolus with other data sets. We're going to do kinetic energy retrieval, but you can actually compare this to potential energy retrieval, which would be through radio occultation, which gives you temperature profiles. And also, because why not, we can use Error 5. Error 5 is a reanalysis model, which means it has a gigantic amount of data. And it's usually very robust when it comes to many phenomena, including gravity waves. Error 5 is actually one of the best models there is for gravity wave representation through many systems such as hyperdiffusion, sponge layer, etc. Point is, we have green profiles here, temperature profiles here and both here. And all these objects are both independent from Aeolus. So I think they are the perfect benchmark for comparisons of patterns. How do you get gravity wave signal from a wind measurement? Well, you know, physics is a lot like cooking. It's very important to follow the recipe. The way it works is you have your wind profile here, and what you're going to do is accumulate all the data within a specific window. So in our case, that's going to be a 5 by 20 degrees over 7 days. You're going to summarize, you're going to average all the data into one big profile. Then you're going to filter it to remove all the small scale perturbation and just end up with a very, very large trend. So you're basically going to get the general dynamic of that area. Then subtract it to your profile, you get what's called the perturbation. This time you do the other way around. You remove the very large scale movements only to get the smaller scale displacement. You're going to do both that filtering at the same wavelength. In our case, that's going to be 9 kilometers. So we want to look at gravity waves that have vertical wavelengths around 9 kilometers. Of course, there's some leakage, but the general idea is to shoot towards that target. And then you simply have to square it and use a smoothing function. And then we're going to focus around, I'm going to say 22 kilometers and the tropopause -1, because this is our sweet spot, and we also want to focus on stratospheric dynamics, and the troposphere might be contaminated with other phenomena we don't want to look at. Another problem is it's not exactly kinetic energy, it's something called EKH loss, because as you remember, this is not exactly U and V components, it's a projection of the two. So what we're going to do is come up with another notation which is similar. And what it means is it's not exactly kinetic energy, it's around 65% of the total sum. But the point is, it's proportional and it's exactly the same. You can find back the kinetic energy simply by assuming you're missing 30%. And when it comes to temperature, what we're going to do from the other instrument, which is radio occultation, it's exactly the same method. So you go through the same filtering, you go through the same retrieval and same averaging, but this time you have the exact potential energy. So that's very interesting. We're going to get two data which use different and independent systems to get at roughly the same stuff. Last but not least important point is how do you correct for noise? Because as I showed you earlier, there's a varying life cycle. The most straightforward way was to simply get the data from both radio sounds and error 5 and see how it changes over time. So what you see here is the difference between each object and Aeolus. And you can see how it goes up in time because Aeolus's noise go up in time. We thought of maybe using radio sounds, but the problem is they are very localized. They might be geospatial biases. So we decided to use error 5, which is more general, more broad. In our case, probably more likely to catch all the issues Aeolus might have. So you can see here Aeolus's average kinetic energy over time, before and after the correction. And now for the big results. So first of all, when I first saw the data, it was a huge relief, because what you can see is that it does make sense. You have a lot of energy around the equator, which is where you have a lot of heating. You have a very strong peak appearing here over the Indian Ocean, probably linked to Madden-Julia oscillation, a known tropical convection phenomenon. And also, these are two different years which show very, very close patterns in terms of seasonality and location. So that's already a very good point. And if you switch to the opposite season, you can see how this time, once again, the correlation is quite visible, but it shifted. And you can kind of see how you have an actual difference between north and south because this corresponds to the heating of the seasons. Yes?
What do you do when it's cloudy?
So in our case, I'm only using wind, I'm going to say, rarely clear data. That means only clear sky. I cannot account for other types. So in our case, that's going to be probably cases where there is no clouds. What I do now is I compare it to GNSS RO. So of course, big disclaimer, kinetic energy and potential energy are not the same, but they are related. Where there is kinetic, you should expect potential and so on. Usually we talk about a ratio of 1.6. I think this is more and more empirically challenged, but the point is there is a direct correlation between both. So you can see here how over the same seasonality, they get the same pattern. So there is obviously something going on here, and I think Aeolus got it quite well. Now what we're going to do is compare it to the big guy. Error 5 is this. Yes?
Like these kinds of figures. So this is averaged over a year, a month?
That's 3 months.
3 months. So 3 months of data, average kinetic energy.
Yes. Yes, sorry, there's many details I go over. The point is, yes, that's basically going to be...
6 to 8, I see, yeah.
Yeah, and you can see that's in 2020, but then you can go over the several years. What I'm doing now is showing an entire year, and I'm going to try to compare this with Error 5. Error 5 is very robust, is very legitimate, so if we get the same stuff at the same place, that means Aeolus did a quite good job. And surely enough, we're lucky to have a very, very good correlation. This is a satellite just, shooting lasers at the sky, and it's getting very good result, very close to very strong models. The point is, if you look at the next year, something interesting appears. While the patterns is very coherent in terms of size and place, it would seem that there's a bit of difference when it comes to intensity. And that raises a question. Which one is lying? Is maybe Aeolus overestimating, even though we try to account for noise? Or is maybe Error 5 underestimating because of its lack of wind assimilation in the data? We're going to need to find a way to tell which one is lying. So another way to look at this is through Hofmöller diagrams. It's very similar to what I just showed you, only represented differently. We're going to look at the 10 minus 10 degree latitude band, because this is where we saw most of the information anyway. What I'm going to do is just display this band over time. And so what you see here, this big shift you see, was just the shifting heat point you saw earlier. And what's interesting here is when you compare Error 5 to Aeolus, you can see it gets pretty much the same data. You can see here and there, it does get the same shift. But what's very interesting is, as I just said earlier, there's a very big difference in its absolute value. Our intuition is that this is convectively generated, and that for some reason, Error 5, because it's over the ocean and there is not a lot of assimilation, especially not assimilation of winds, gets it wrong. So the way we could do this is to use OLR. Outgoing low-wave radiation is proportional, or should I say inversely proportional to convection, because it goes from the Earth to space. But if there's clouds, you'll get less outgoing low-wave radiation. And the thing is, the more convection you have, the more clouds you have. And when we overlay the lowest OLR values, what do we get? We get a perfect overlap with our heat points. So that means, quite likely, what you're seeing here are convectively generated gravity waves. What you can see is that Error 5 does get it, but only so slightly. So there might be a big lack of wind assimilation in that area. Another thing we can do is maybe ask ourselves, okay, maybe that's just a general convection-linked problem that might also be seen in other channels of Error 5. So what about potential energy? And what's very interesting is that this time, Error 5 gets it completely right. It does get the right value at the right place at the right time. So you can see this is clearly not a problem from a physical standpoint. Error 5 is able to resolve quite clearly the phenomenon on the potential energy component, but not on the kinetic part. So I think the big conclusion here is that there is a lot of missed opportunity when it comes to assimilation. I'll conclude on that part of the talk just by saying that we used data from the radicular channel of Aeolus to retrieve kinetic energy from gravity waves, both inertial and inertia. But what we showed was that there were very cohesive, coherent, and seasonal patterns appearing, and that they were also very coherent and correlated with GNSS-RO and Error 5 derived elements. The hotspots, I think, were primarily linked to convective phenomena, such as the Madgen-Julia oscillation, based on the low OLR measurements I showed you. I think this whole presentation is also about how I think Aeolus can be a new data source to study convection-induced gravity wave phenomena, especially in poorly assimilated tropical regions, such as the ocean, I haven't talked about it, but there's a lot of studies explaining how over the ocean, there's a lot of increment, which means there's a lot of correction of the models when it gets real data. And I think this is just a goldmine of information we haven't touched yet. Another way to look at it is when we try to look at the perspective and the numbers, in forecast, only 0.42% of the data was coming from Aeolus, but that had an impact of 2.3% of improvement in the data. So you can just see how much models right now crave for more precise wind information. The same goes for DCMWF data. Another thing we can do is look at the legacy of Aeolus. Aeolus is actually kind of a success in the sense that it created enough excitement for Aeolus 2 to be decided and funded. It's probably going to launch in 2030 something. The point is it's going to be a constellation now with much higher laser power, a greater precision, and more operation lifetime. And my small and modest recommendation, if they go for the same system, would be to increase the signal-to-noise ratio, because that was really a limiting factor for us. It was very hard to go above 22 kilometers, and I really wish we could have, because this is also where a lot of dynamics gets interesting. And another problem I didn't really mention is how the RBS, so that's the vertical resolution setting, is something that has a huge impact for us. That's going to sample differently the data, that's going to change how we perceive waves, and we need a way to make that more consistent and constant over time. So it would be very nice if in the future there would be such a thing as a RBS for gravity waves that would be strict over specific places. And also we must address more clearly in the future metrics for instrumental errors, such as the oscillations I've shown you and so on. Okay, I'm gonna try and wrap this up with my more recent work at Miami, which is in some sense different but quite close, because I'm looking at waves again. Only this time I'm using a different perspective. I'm looking at cloud top convection from geostationary satellites. If you stop in the image for a second, I think we can all see waves going on here, probably here. And I guess it's very easy for us humans, right, to see something here. The problem is, can machines do that? And if they do it, has it been done before? So when Brian was writing this proposal, he did his research, and actually we have decades of imagery of low clouds over the damp subtropical ocean, but it's not really used for gravity wave analysis. It's mostly used for radiative transfer calculations. And I think we're sitting on a gold mine, because there's so high contrast between the very dark areas, the very bright clouds, and the modulation of those through the waves. That is probably a way to retrieve the visual signals from this to create a more bigger observatory for gravity waves. So that's basically the project. You give me an image and I'll tell you where the waves go and how big they are. What do we really want from a wave? I think we can boil it down to three main components: the wavelength, the speed, and the direction of propagation. How does it work? You have your image and you're going to do what's called a wavelet transform. I'm going to explain that in details in a second. But the point is, you're going to end up with a 4D matrix. You're going to get the 2D components of the map, you're going to get the scale, that's how big things are, and the angle, which means the direction. I'm going to cheat a bit. This is a 4D array, but you're never going to have to look at it 4D. We can cheat out 2 dimensions each time to do maps. You'll see it's actually quite intuitive. So how does wavelet analysis work? I'm not going to go through the mathematics, because I think this is maybe not the big point here, but intuitively speaking, it's kind of having this sort of a microscope. You're going to make the wave go through the image, and based on a specific scale, you're going to fine-tune it to find specific sizes of objects. So in our case, we have a very well-defined object here, which has a specific scale, and we would like the wavelet to only focus on such sizes. So what you're going to do is, as an example here, you have the Mexican hat function, which is very good for sharp edges. And the point is, you can deform this wave over time to make it either thinner or bigger to focus on specific sizes. As an example here, for scale 3, you can see the response of the data. So that would be on a 2D map for a specific scale, and you can just see how it gets the data right. Problem is, this is isotropic, which means there is no possibility to factor in the angle. And that's a problem, because we would like to get the angle right. What we can do, luckily, is anisotropic wavelets. It's the exact same idea, except there is a sensitivity in how you use the angle of attack. There is a asymmetry in how the wavelet is which means based on if you throw it like this or like this, you're not going to get the same response. And that's perfect. That's all we need. We have an object that allows you to look at the direction and the size. That's probably well enough to get on the first test. So if we get back to our example, we have this 2D image. You do the transform. What do you get? Let's say we merge all of that into a single point. What you could get is this wave rose plot. So the way you read it is like so. The scale gives you the radius. So the further you are from the center, the bigger your object is. The angle gives you the propagation angle. So that kind of represents the real life angle of the object. Okay, so it means it's going this way. And the color means the detection strength. So the more color there is, the more signal there is. So the way to understand and read this is, oh, okay, well, you have two waves. You have one wave going this direction at this scale, and one wave going this direction at this scale. One thing we could do is, well, okay, we only have one frame, but what if we use a video? We get subsequent frames. And maybe, just maybe, I could get the speeds of those objects. So that's what we're going to do. What you can do is called a cross-wavelet spectrum. You're basically going to multiply the wavelet transform with its conjugate, and that's going to give you the cross-wavelet spectrum, or the coherence. That means that for a given scale and angle, you're going to get these colors, and the stronger the color is, the more coherence there is on such objects between two frames. It means there's a very high likeliness that what you're looking here was also present on the previous frame. And the point is, okay, well, I kind of know that there's an object here that I'm tracking. It would be interesting to get the phase difference, and you can actually do that if you apply the masking of those coordinates on the phase difference, which is basically just the difference of the phase between the two frames. You get this phase shift. The phase shift, since you have the scale, you can transform into a displacement. And since you know the time between each frame, you can actually calculate the speed. So in our case here, you have a specific phase that you can then change into a physical shift, which you then bring into a speed. So what we can do is put even more information in our previous plot, because the horizontal component was redundant anyways. What we can do is use the lower part for another thing, which would be the coherence, as I showed you. Red means there's nothing to see. Orange is there's a very high likeliness of similar objects. The peaks here are represented with the small stars, and the values here represent the speed. So that's the best way we have to convey as much information as we can in as little dimensions as we can. I'm going to try and make a more visual example for you guys. So in square 17, you have this very visible object here, this kind of wave moving this way. What would be interesting is to see if our program gets it, and if so, could it give me the wavelength and the speed? So that's going to be our usual suspect. In our case, if we look at this square, it's probably going to be something around the bottom right. We're going to see if it gets it. So I'm going to go back to the algorithm real quick. You get the image, transform it into a rose plot. You get the cross-wavelet transform, which gives you the coherence. The coherence gives you a map that you apply on the phase. The phase gives you the shift in terms of distance, and then you get the kilometer conversion. So you end up with the same thing as before. So what does it tell us exactly? It tells us we have two objects. One here, I'm going to show you the conversion from scale to kilometer after, but keep in mind we have a small object here at around 12 meters per second, and another one at 8 meters per second. Okay, but that doesn't really tell me if it's physical or not. We need to visually see it. So a way to see it is to map the real and complex part of the waves. If we look at the one on the right, the magenta masking here represents the area of coherence, so basically the area where you have to look. So the first suspect on the right does get some variance. You can see there's a black, white, black pattern, which might be a section, a big wave. In any case, that's not really what we're interested into, so I don't think that's what we're looking for. But if we look at the second one, the subject on the left, well, you can see that's pretty much what we're looking for. You have this very small periodicity. You can see the magenta masking here means it's very certain that this object is moving and present in the subsequent frames. you can see it gets a very realistic wavelength for around 80 kilometers, and also a very credible speed. 11.7 is close to the expected, 15 meters per second you would get. So that's not so bad. Or how we say, I think you can see here again the correlation between both, which is quite good. So I wouldn't say it's not so bad, or how we say in French, c'est pas mal. And I think I'll just conclude by saying that I'm used to see a lot of models, system, theory. I come from a more experimental background, and there's a very nice quote from Jacques Blamont that worked on my previous department, which was, a well-done, well-documented measurement will survive, and the models that try to account for it will pass. I think it's a bit provocative, but the point is we're sitting on decades of information, and that information is real and true and to be trusted. And if we're able to use it, that's a mountain of assimilation we could use for next generation models. And even the models after that, the point is, this is empirical truth, and as far as it goes, I think it is understated and underused in modern science in my field. And I'll just finish by showing you this very nice picture, which is the team I used to work in my lab back in the days in French Algeria, when they lost the first French rocket and they came up with the lidar system and ideas. And decades after that, it ended up with Aeolus, which is in some sense a very nice way of showing how science is also about human adventure. And with that, I'd like to thank you very much. Yes.
To show the highest resolution animation or movie of the clouds.
Yeah.
You had a lot of filter. Yeah, not this one.
Oh, this one you mean?
Couple backward.
Oh, you want the more?
This is pixel. Yeah, this one. So here you have, just my eye, right, sees the waves, but they are also convection cells, coherent structures, right?
Yeah.
So how do you differentiate the two?
Okay, so that's true. You have a lot of problems. The big one is you have advection, so you have the displacement of the wind itself. Well, one thing you can do is, of course, look at the contrast of colors, but that might not be enough. So another thing you can look at is the convergence and divergence of the signals. So as you can see, waves, when they go, they tend to...
What do you do with the cells?
So at the moment, what you can do is called PIV, so particle imagery velocimetry. And you can treat the image to only focus on places where you get a logical coherence, divergence, etc.
Okay.
So I would say extra treatment. In itself, wavelet might not be enough, so you have to think of extra layers, yes.
Right. And then also in the large picture, I mean, what is the downstream uses of the waves information, once you have the waves information?
Okay, so what could you do? Well, another problem today with parameterization is, we put waves here, but it's hard to say what generated it. Was it a wind shear? Was it a volcano? So the point is, if I can give you a climatology of decades, I could say, well, okay, I'm going to look at all the cases where there was a nearby explosion that day and see if I always get the same wavelength and the same direction. Then maybe, just maybe, that means that this wave was generated by the volcano. So the overarching idea would be to help parameterization and understanding of generation of gravity waves.
Sorry, one more, just curious.
Sure, be my guest.
Like they used to talk about form drag. Do you worry about the total form drag, like topography?
So,
topography?
Yeah, well, topography in our case would mean recurrent waves at specific times at specific areas. At the moment, we're just tracking special patterns in specific areas, and that's just a test case. In the future, we'll probably have to think of a way to factor in topographic and not. But that's, I'm going to say, a challenge we haven't tackled yet.
Okay.
Yes.
So thank you for a very nice talk. I like this about the gravity wave. I have a question about where you showed some slide before the Howmoller plot.
Yep.
In that you showed gravity wave kinetic energy over the Indian Ocean for summer and winter season.
Yeah. So here?
Yes, this one. So my question is, it makes sense to me during JJA over the Western Indian Ocean, Northwestern Indian Ocean, you have very like the high energy. But what happened in the SON or over during DJF over the maritime continent where we have this Indo-Pacific region what is happening there? Do you have any explanation?
Yes, yes. I'm going to switch to a backup slide, which is in French, so I have to translate it, but don't worry about it. So, just let me get to it. So, we suspect this is something called a... That's probably Baden-Julian oscillation. So what this is a very known phenomena. That's a atmospheric circulation within the equator region and over the tropics. So it's kind of a 6-stage phenomenon where you have anomalies of temperature, which means convection and precipitation, which means ocean atmospheric coupling. You then have pressure anomalies, which creates winds, upward motion, generation of waves, which is what we see here, and then downward motion. And basically, that whole cycle moves toward the east. And that probably explains why you have this shifting pattern over time. But what's also important to remember that this is only cycles from 30 to 60 days, whereas what we see is actually much bigger in terms of time span. So our intuition is that this is the catalyst for waves, but its long-term impact has a much layer-lasting signature on the signal. But that is the main culprit for this shift eastward in the signal, I would say. So as far as I know.
What time scale will be this phenomenon? What time is the
So that's from 30 to 60 days, the whole movement and cycle. But if you go back to the pictures, what's interesting is it's actually much longer than that. It's like 3 to 6 months. So there is some questions about maybe this kind of I would say a catalyst, but then the system itself keeps on going for a few months.
And another point you made, the RF5 data underestimate this.
Yeah.
Right? And it makes sense because the RF5 is like the reanalysis part, it just comes with the model plus observation.
Yeah, and it's
Has own
thermal
biases.
wind. Yeah.
Yeah, so we don't really, it's good if they capture the same magnitude, but we don't expect that because it's just a reanalysis.
Of course, and the thing is, RF5 was called thermal wind. It's just thermal information through equations creates back the wind, which is broadly different from real life wind. And this is just one of many examples that RF5 is not the best for wind.
Thank you.
But, sorry.
Yes.
On this point, but your temperature comparison was good, right?
Yeah, it was very good because I forgot to mention that RF5 assimilates GNSS-RO. This is all assimilated. I mean this one.
It's influenced by assimilation.
So you would not expect a lot of difference because it's all weighted towards these results. But the point was trying to show that there is no specific difficulty around that area. If you have enough assimilation, you get it right. Yes.
This is really great.
Thank you.
How do you account for, I guess, what I would assume would be a lot of missing data or missing times that you can't use because it's not cloud-free, whereas in Era 5 doesn't care about cloud-freeness unless you do somehow take that out to match the cloud-free days. Like what's the missing data?
Yeah, well, that's a very good point. Is you have to make many compromises, especially because what you have to do is bring Era 5 back to the H-loss projection, which in itself is its own thing. I think maybe I have it somewhere here. Yeah, I think that's a good one. So I kind of try and compare Aeolus 8 EK to GNSS-RO, then I compare Era 5 EK to EP, and Era 5 EK to its projection. So I try to see, okay, what am I losing? Am I losing a lot when I convert from normal to H-loss? Is the ratio from Era 5 similar to what you would get from Aeolus and GNSS-RO? And the point is, of course, Aeolus doesn't get all the dynamics, but the point is that when it comes to the locality, it's actually quite good. So once again, I'm comparing apples and potatoes, but if you stray away from the objects and the values, but look at the area, I think it's quite good.
Any more? Or, thank you, Mathieu.